My name is Gabriel State. I'm a Senior Director for Simulation and AI at NVIDIA, and I manage the group that does the Isaac Gym system. I'm going to take you through a bit of an introduction to Isaac Gym and some of the motivations and some of where it fits in with the rest of what NVIDIA's simulation group is doing. And then all of the people who know more about the technical details than I do are going to jump in and tell you more interesting things. If you have questions, we do have the Zoom chat. So our preference is that you use the Zoom chat to ask questions, and we'll try and answer them as we go. Ankur or Victor, I'd recommend if one of you can watch the chat as I'm speaking, I can do a couple minutes of Q&A after the fact. Just let me know at the end, and I'll speak to some of those questions, and then we can do the same in the other presentations. The motivation for Isaac Gym is all about reinforcement learning, and reinforcement learning, as I expect that pretty much everyone who's attending this knows, essentially consists of simulating an environment, observing things that are going on in that environment, and then having an agent that excuse me, that acts on that environment. Typically, the way that this has happened up until now has been with CPU-based simulators. You'll have your environment simulation happening, typically with physics running on the CPU. You will usually have rendering running on a GPU if rendering is important for a simulation. However, not always. We know of folks who are doing rendering on CPU as well. Then the results of the environment simulation are then processed through reward and observation calculations. Those are both saved to a rollup buffer as well as passed along to a policy network whose job it is to make the observations and decide on a course of action. That policy network might run on the GPU or it might run on the CPU. And then finally, that policy network, the result of that policy network is used to generate some action. The action is also saved to the rollup buffer. The actions are then brought back into the environment simulation for the next round. Periodically, you take your rollup buffer and you run your R algorithm, training a value network and a policy network, and periodically updating the policy. That's typically how things are done today. What that means, unfortunately, is that most RL that's happening today is relatively slow. Your physics runs on the CPU, your observation and word calculations run on the CPU. You may have to transfer data over to GPU. You can use multiple threads to speed this process up. However, that only gives you a limited amount of parallelism, and you have data transfer back and forth from the GPU to the CPU. So it's fairly limited in the speed ups it gets you. What we really want to see is parallel simulation. So this is really when we started looking at what we wanted to do with Isaac Gym. We started looking at this question of how can we make use of the GPU most effectively to simulate things in parallel. So that's really what our focus has been. Run a large number of environments simultaneously, take a large number of actions simultaneously. We started looking into this back in 2018. Jackie, who's here with us, or at least has a recorded presentation for us, along with Victor and several others, began experimenting with this idea of making use of the GPU for simulation using our Flex physics engine, which was a experimental physics engine that we use for research internally. And we published a paper on this showing some really good results combining CPU accelerated physics with reinforcement learning. We then followed it up with our first iteration of Isaac Gym in 2019 that we shared with a small number of researchers, where we put all this together into something that, that could be used for reinforcement learning research. So we put together an asset loading pipeline that allows us to import URDF or Mujoko environments. We have an API for setting up the environment. We have Vulkan-based rendering. We're using, in this case, PhysX, not fully accelerated, or Flex. So in this case, the API being used to set physics state is running on the CPU. However, the physics itself is running on GPU. So we use this for internal research. We're doing a lot of research on animation. It's one of the topics that's very much of interest to our simulation group. And this is an implementation of the deep mimic algorithm by Jason Peng and others that we did with this prototype. So in this case, this was our first attempt where we said, all right, well, what happens if we run physics on the GPU? And we got some really good results. However, it was not fully accelerated. With this setup, we actually still have data transfer issues, because while simulation happens on the GPU, we then had to transfer data back. We had read back from the GPU, excuse me, to the CPU to allow observation reward calculations to happen on the CPU. And then we'd have to pass the data transfer. We'd have to pass the data back to the GPU to run the forward pass of the neural network, and then pass those results back to the CPU in order to apply the changes to the physics state through a CPU API. So last year, we began to look at how we could eliminate all these bottlenecks and bring everything over to the GPU. So this is the goal that we set for ourselves, and that we're able to achieve. And I'm happy to report that we've been able to have significant improvement in a lot of performance using this method. So in this case, everything happens in the GPU, including the data passing back and forth between simulation and reward and observation calculations. So physics happens on the GPU. All that state stays on the GPU. Reward and observation calculations are written using PyTorch JIT functions. Those are JITted to GPU code and directly take the buffers from the GIM simulation as input. The output of that is passed directly in the GPU tensor along to the network, and then the action, again, there's a GPU-based API for setting the actions as well. So we have a complete end-to-end pipeline. So this has been, I think, transformative in terms of how we've been able to accelerate complex RL work on the GPU, and we're really excited that we're able to make this available. So we did our first public release in October last year. We've been continuing to work on it. So again, physics is running entirely on the GPU. The results are stored in PyTorch tensors. We have tensor-based APIs for looking at the physics state and getting at the data you need for the observation reward calculations. We can run thousands of environments simultaneously. We have APIs for physics-based domain randomization, force and torque sensors, Jacobians, mass matrices, inverse kinematics, and there's some cool stuff to show you. We will show you later on operational space control. One thing I'll note here that I'll talk about a little bit later is that what you're seeing rendered here is actually being rendered using our Omniverse system. And I'm going to get into Omniverse in a couple of moments. But what we've done is we've run in the Isaac GIM simulator, and then the results of that are saved out to USD, which is a format that I'll talk about shortly, that we can then render inside Omniverse for some really great looking results. So this is an experiment that we ran duplicating work that OpenAI showed in late 2018, where the shadow hand is manipulating the cube and matching the pose that it's given. This is being run with domain randomizations of not only all the masses and friction properties of the hand, but all kinds of other randomizations of mass of objects and so on. Victor will go through more of a list of that. So each one of these is separate. There's a single policy that's being trained across all of these domain randomizations. The policy is as robust as possible. So this is duplication of work that OpenAI did a couple years ago. They used a 6,144 CPU core cluster, 384 machines for this. It took approximately 40 hours of training with a relatively straightforward feed-forward policy and value networks in order to achieve a rate of about 20 consecutive successes. We're able to do that now in 1 hour on a single GPU. This is transformative for being able to do physics-based reinforcement learning research, because now you can iterate really quickly. You can see the problems with your policy. You don't have to wait. You don't have to have access to a massive cluster like that. Individual grad students can do a lot of work just on their own. So we're really happy about this, and Victor is going to get into showing you more about this shortly. We've been using this for other work. So I mentioned animation is something important to us. So this is a paper that our Toronto-based AI research group put out last year called Unicon. This is a network that takes a motion capture sequence as input and simulates the character physically with essentially corrections against what's happening in the physical simulation. So this allows the network to replicate a given pre-recorded animation, but do so with proper physical interaction. There's a lot of work going on in this area. Jason Peng has been working on some things with us this summer, implementing his AMP-based animation system. AMP would typically take 1 to 2 days on a CPU to train a given animation, and we're able to do that with Jim in about 10 minutes at this point. So we're hoping that we'll be able to release some of that code later on in the summer. The last release of Isaac Jim, we added a couple of sample environments. So this one is the Ingenuity helicopter. We were inspired by the recent Mars rover and helicopter landing. And this is a super simple policy that just has 2 disks, one above the other, that exert force, and we were able to train it to move to a target location. This video doesn't show the target location. We train it to move to a target location, and again, we can train that in just a handful of minutes. So another thing that you're going to see today is some of the work that we've done on sim to real. So we have a lot of folks within NVIDIA working on quadrupeds. A lot of the RL policy work is happening inside Jim, and we do transfer, we demonstrate that we're able to transfer that work to the real world as well, and it works quite effectively. So some of that is based on the domain randomization work that we do, and some clever work by our researchers. Right. So before we get into the rest of what you're going to hear about today, getting into the details. One thing I wanted to share was where this all fits with the work that NVIDIA is doing overall in simulation with our Omniverse system. Omniverse is a simulation engine that NVIDIA has been working on for quite some time. That's at the core of a lot of the work that we're doing internally and that you'll see from us going forward. The idea of Omniverse is to have a universal platform where we can take open standards such as Pixar's USD, our MDL, material definition language, the work we've done with PhysX, and put that all into a single place that then can connect to 3D-based tools from everywhere in the world. We've released open beta versions of this. There's more coming soon with exciting physics-based features, which I'll tell you about later on today. But this is a really key platform for a lot of the work that we're doing going forward. It's all based around USD. USD is a technology from Pixar, which essentially represents complex scene graphs. It's about the 4th version of such a scene graph system and API that Pixar's developed over the course of their work on all their movies. And it includes a concept of layering, which is quite similar to what you might see in an application like Photoshop, where different layers can be on or off and can be added or removed dynamically. One of the things that this means is that you can actually have large teams that work together to build up scenes. You can share assets from just about anywhere. You can have different groups working simultaneously on even the same files using our Nucleus system. And we're seeing this quickly becoming a standard outside of the media and entertainment business. We're seeing it being adopted all over the place, and we're talking to a lot of people about why we think this is going to be super valuable for a lot of simulation. One of the things that we've added to it has been physics support. So that's now been adopted into USD as a core part of the library, and that's in collaboration between ourselves, Pixar, and Apple. So we foresee USD as being kind of the equivalent of HTML for 3D worlds moving forward. So by having USD as the basis, we can then build connectors to existing 3D tools and bring all that content in. One of the pieces that we have within Omniverse is a Nucleus Server. This is essentially a place where the USD files all live. And when an Omniverse client connects to a Nucleus Server, it can actually have live updates. You can have multiple people working on the same USD scene at the same time. And then because it's an open standard, there are a variety of different ways you can then process the USD information. If you want to render it, we have our RTX renderer, but there are also other renders out there. We're building, as I said, quite a bit of our future technology on this. So Omniverse Create is one of the pieces that's out there now that folks can download if they're interested in looking at this. This is an application that takes the components of Omniverse that we think are useful for designers and artists, but we have many others. We have Machinima, which is an application for developing animations. We have Omniverse View for visualization for the AEC community. We have Omniverse Kowlin, which is designed for 3D deep learning research. So we have a lot of exciting research going on in content creation using deep learning methods. And we have our Drive Sim simulator. That's another one of the groups that I'm deeply involved in, and folks on my team are involved in to build driving simulators. And then last but not least, we have our NVIDIA Isaac Sim robotic simulator as well. So Isaac Sim, I'm going to show you a quick video of Isaac Sim. one of the things I'd like to make sure that folks understand is the distinction between some of the different Isaacs that we have, because it can be a little bit confusing. Isaac Sim is our simulator built on Omniverse that that we share with folks who are doing industrial robotics. It closely connects with our Isaac SDK, which is an SDK for those kinds of industrial robotics projects that includes various pieces for autonomous navigation and sensing. It includes things like LiDAR sensors and a variety of other elements that make it really good for these kind of industrial robotics projects. The work that we're doing in GIM, we are in the process of moving a lot of the work that we're doing in GIM into Isaac Sim, and I'll be telling you a little bit more about that later on this afternoon. But that's where the distinction are. So we have Isaac Sim, which is the Omniverse-based industrial simulator. We have GIM, which is most of what we're talking about today, which is our RL simulation environment for research. Isaac SDK, which are a group of APIs for running on actual robotics. All right, and that's it for my presentation today. I can take a couple of minutes for questions, though. Actually, if there are any questions, I'll take one or two, and then we should move on. But just before I do that, I want to just give a shout out to a large number of people within NVIDIA whose efforts have brought us to this point. Not everyone is here today, but it's been a tremendous effort by a lot of people to bring things together, everything from the physics side of things to all the plumbing work and connecting with Omniverse. So kudos to everyone involved. And thanks very much. Victor, do we have any questions, or should we move on to Lucas?
Just a quick question at some point. Is this open sourced? Although I'm not sure which pieces it was referring to, because Gabby, you were talking about a bunch of things. So maybe just make that clear for people. Yeah, so the system as a whole is not open sourced. So there are some pieces that source is available for. So for example, within Isaac GIM, there's source available for all the components at the Python level, which is above the physics simulation and environment setup portion. So everything that's in there is source available, and we are going to be making more examples of usage open source. And I see another question about the physics engine that GIM uses. So Isaac GIM supports both Flex as well as PhysX. So Flex is the engine that we've used for research for some time, and PhysX is our production engine. So everything you're seeing inside Isaac GIM is based on our latest internal PhysX. So in fact, that's actually one of the places that you can see some of the PhysX stuff earlier than elsewhere, and that same PhysX is what's used in Omniverse. All right, I'm going to pass over to Lucas so that we don't lose too much on time.
Okay, so hi, my name is Lucas. I'm one of the core engineers on Isaac GIM, working on the overall API, but in particular on the Tensor API for end-to-end GPU acceleration and stuff like this. So in this presentation, I'll give you a brief overview of the API, basically. So enough information to sort of get your feet wet. It's not an exclusive, like an all-encompassing view, because that would take too long. We have documentation for all the details, but just the idea is to tell you how all the things fit together, establish some terminology and things like this. So like Gav mentioned, with Isaac GIM, the idea is to be able to simulate multiple instances of some environment in lockstep. So here we have, like in this image, we have 64 environment instances, but we often go to tens of thousands of individual environments of varying complexity. So the environments are physically independent of each other. They all have their own local space where, that's where you get all your transforms. But we render them together so that you can easily see what's going on overall, right? Like if any environments are exploding or misbehaving or something like this, you'll be able to see it right away. So within each one of those environments here on the screen, there are 3 actors. So actors are like the main building blocks of the environments in Isaac Gym. And so there's a Franka robotic arm, very simple table, which is just a static block, and a little box to be picked up. And then we have a simple API for setting up these environments, adding actors, loading assets. And then once the simulation gets going, you interact with it using tensors. And this is what I'll spend most of my time talking about. So each actor can be a single rigid body, or it can be a multi-body actor, right? And multi-body actors are the more interesting one, because usually things that you can control are articulated entities. And so these are created as a reduced coordinate articulation in PhysX. And what that enables us to do is that you can work with the actors in maximal coordinates, so in terms of all the rigid bodies or articulation links, or reduced coordinates, so it's all the degrees of freedom, right? So for this Franka actor, there are 11 rigid bodies or articulation links. There are 10 joints, but only 9 degrees of freedom, because one of those joints is a fixed joint. So Isaac Gym gives you the API to work with either the bodies or the degrees of freedom, or DOFs. So when we control an actor like this, you can apply torques or forces for linear degrees of freedom. You can set PD targets, so position or velocity targets, and you can also apply forces and torques directly to the bodies. So first, a little bit of code. So everything comes in an Isaac Gym package. There's a couple of different modules there. So the Gym API is the core API, and then there are some other utilities for, let's say, PyTorch interrupt, so you can actually get all your tensors in PyTorch, and that's the Gym Torch module. When you're creating a simulation, you can set up a lot of different simulation parameters. Basic stuff like delta t, right? So the amount of time to use for each substep. But you can also set various PhysX parameters to really control the simulation. One of the most important ones is whether you want to run the PhysX simulation on GPU or not. And that's obviously important for having a full end-to-end pipeline. So yes, we want to use PhysX on the GPU. And then very important parameter is whether to enable the GPU pipeline. So the GPU pipeline parameter does a number of things. First of all, it enables you to get all of the physics state tensors on the GPU without any readback to the host. And it also enables you to apply control inputs in GPU tensors without that data ever being moved between devices. So you set up your simulation parameters, and then there's a create sim function, which takes a few arguments. You can specify the rendering device and the compute device. Those are the first two parameters there. So you can actually, on a multi-GPU system, you can run the physics on one GPU, and you can run all the rendering on another GPU. You specify the physics backend that you want. In this case, we're interested in the PhysX backend, because the end-to-end GPU pipeline is currently only available with the PhysX backend. You pass your parameters and you get a new simulation object. So initially that is a blank simulation, and then we have a very simple procedural API for creating all the environments. Before you create the environments, usually you want to prepare all your assets. So an asset is basically like a blueprint for an actor that you will later add to an environment, or instantiate multiple times in the environments. So we support loading things from URDF or MJCF. And we also have, you can create very simple assets like, boxes or spheres using like a simple direct API, right? So you can load an asset from a URDF for the Franka, and you can create a simple box to be picked up just using this procedural approach. So Here, I'm going to skip a whole bunch of details which are covered in the documentation, but basically you will loop over all of your environments. You will create each environment individually, and then you can create actors in a specific environment by basically making an instance of an asset. So it will make a separate independent copy of your Franca in each environment and make a box. Typically, what's usually done here also is that you can set up all of the initial poses. You can configure all your joint drives and stiffness and damping and other parameters, physics materials. You can customize or randomize things like friction, restitution, that kind of thing. And then very importantly, if you're using the Tensor API, once you're done setting up your environment, so you've created all the actors, everything's ready, before you get into the main loop, there's this gem prepare sim function. And that just sets up some internal buffers, allocates various internal things, and the storage for the tensor on the device that was chosen, right? Whether we're using the GPU pipeline or the CPU pipeline. This just sets everything up. So a little bit more about these tensors. So Isaac Gym uses global tensors. And what that means is that you can have a tensor with all the rigid body states in the simulation, and that is just essentially a single array. So there is, the environments are laid out sequentially in memory, right? It's all part of the same tensor. And for, let's say, all the rigid bodies in each environment, they are also laid out sequentially, right? So for Franca, we have 11 rigid bodies. So there will be 11 rigid bodies in memory, and then a slot for the table and the box, and that makes up one environment. And that's basically replicated for as many environments as you have. Now, in this case, this is the rigid body state tensor, and rigid body states are made up of the position, which is a 3D vector, the quaternion, which gives you the orientation, and linear and angular velocities, which are 3D vectors, right? So yeah, so essentially all of these floats, all of these bodies are laid out in a single tensor, and you can access everything through an index into that tensor, which you can also query using the API. So there's a number of different state tensors that you can access. So each actor will have a root state, which is basically the state of the root rigid body. So that essentially defines the position, the orientation, and the velocity of each actor's root body. So by setting these values, you can basically teleport actors around without changing all the child articulation link poses, right? So for articulated actors, if you want to actually change the child link poses or joint poses, I should say probably more accurately, we use the DOF state tensor, right? So it's the tensor that describes all of the degrees of freedom in the simulation. There's also a rigid body state tensor, which has all of the rigid bodies, not just the actor roots. You can set up various force sensors in Isaac Gym, and you get all the readings through these state tensors as well. So there's a force sensor tensor for degrees of freedom, a force sensor tensor for rigid bodies, which gives you the forces and torques experienced at some particular location on a rigid body. We have a contact force tensor, which reports all of the contact forces experienced by each body. And then we also have some specialized tensors for Jacobian matrices and generalized mass matrices, which are useful in NIK or operational space control type algorithms. And you can get those on both CPU and GPU right now. So all of these are available on both CPU and GPU, depending on the pipeline that you select. Now for control, like I mentioned already before, you can apply forces. So there's a DOF actuation force tensor. So you can specify actuation forces for each degree of freedom in the simulation, or you can set position targets, or you can set velocity targets, depending on how you've configured those individual degrees of freedom while you were setting up your simulation. You can also apply forces and torques to rigid bodies directly. And so to actually access those tensors, I'll talk about the API for doing that. So Isaac Gym is implemented, the core of the simulator, everything's implemented in C++ and CUDA. So we basically deal with raw memory buffers on either the CPU or the GPU. And we have functions that allow you to get what is essentially a tensor descriptor. So you can acquire the actor root state tensor, and that returns the tensor descriptor, which describes the data type, the shape of that tensor, and a pointer to the memory location, which you can't really directly use in Python. So those objects on their own are not super useful unless you're actually doing this in C++. Most users will be using Python, and so in order to expose these tensors to Python, we use various wrapping utilities. And so we have let's say the root state tensor, and if you want to get it in as a PyTorch tensor, there is this GymTorch utility where you can wrap your the raw Gym tensor and get a PyTorch tensor. So here we're creating the root states and DOF states in a PyTorch tensor. It's not actually making a copy of it. It just kind of wraps the memory that Isaac Gym holds to have all of these different states. And then once they're wrapped, you can treat them just like a regular PyTorch tensor. So you can set up different views, you can set up different slices. Usually you will want to create a view that you can index using the environment index. So one of the dimensions will be the environment index, right? And then you can get particular slices. So let's say for the root states, they capture the state of the root rigid bodies. So you have 3 floats for position, followed by 4 floats for quaternions, followed by linear velocities and angular velocities. And you can basically get PyTorch slices of these tensors. For the degrees of freedom, for the DOF states, we have the position and velocity, and these are just single floats. So for linear degrees of freedom, the distance units are meters. For the rotational degrees of freedom, the distance units are radians, right? So positions are in radians, and velocities are in radians per second for the degrees of freedom. So once you have your PyTorch tensors, they won't automatically refresh. So your main loop, where you will call the Gym simulate function that actually advances the physics simulation by the delta t that you've specified in the simulation parameters, it will advance the simulation, but we don't automatically copy the data into those tensors. And that's actually by design, even though some people have found this feature a little bit clunky because it's easy to forget. The reason is that the state tensors are not actually the very same data as the physics engine holds. And that's because Isaac Gym provides a data abstraction layer over the physics engine itself. So you can run the simulation in PhysX or in Flex, and they use very different internal layouts and data structures for all this stuff. But for consistency, we want to present a stable, simple API for users in Python. And so we actually do make a copy from the raw physics engine data into these Gym tensors that you can manipulate in your scripts. And we don't automatically make those copies because sometimes you don't necessarily want to make those copies on every simulation step. And so, for example, you might want to get the Jacobian matrices every, 10 simulation steps, not on every single simulation step, in which case, automatically copying the data from the physics engine to these state tensors would be wasteful. And so for performance reasons, we require that you actually manually refresh all the tensors that you're actually currently interested in. So you have to call these like tensor refresh functions, right? And so once you refresh those tensors, all of those PyTorch tensor views and slices are updated with the very latest data. If you want to apply controls, typically you will compute, let's say you want to apply DOF forces, or torques. You will typically compute this based on actions recommended by the policy of your agent. Here we're just really generating just a tensor full of random values using torch, right? So we're just creating a torch tensor. And in order to actually apply those values, we need to pass that to GEM. Now, because GEM doesn't, like the internal simulator, it's not linked with PyTorch in any way. It doesn't know anything about PyTorch tensors. So just like you have to sort of wrap these GEM tensors into PyTorch tensors, you have to do the reverse to actually pass your PyTorch tensor into GEM, right? So there's an unwrapped tensor utility, which will take your PyTorch tensor, create a GEM tensor descriptor that GEM can understand, and then you can set the DOF actuation forces using that wrapped tensor. So yeah, you can apply forces or set PD targets. So you can set position or velocity target tensors as well. Typically, you won't be intermixing them for the same DOFs, but you can actually have some DOFs that are controlled using actuation forces and other ones that are controlled using position or velocity targets. And GEM should be smart enough to figure out which control input to apply to each DOF depending on how you've configured it beforehand. Okay, so let's look at a very simple RL example. And so, I mean, there's nothing more simple than cart pull, and it's an example that everybody will be familiar with. So you have a rail, you have a cart that slides along the rail, and a pole which is free to rotate about the cart, right? And the whole point is, hey, you got to push the cart so that to maintain the pole in an upright position. So it's a very simple system. There are three bodies: the rail, the cart, and the pole, and there are 2 degrees of freedom. So there's one linear for the cart and one angular for the pole. And then the whole system has a fixed base, which means that that rail just kind of magically levitates in the air. It's sort of attached to the world in a magical way, so it doesn't fall down. And so there's a way to do that. You can have fixed base actors in Isaac GEM as well, right? So this is a perfect setup for using the controls and state using degrees of freedom only, right? Like there's no reason really to know the quaternions that are involved or the 3D positions of the cart, because everything can be described using just 2 floats, right? So the first degree of freedom has the cart position, right? It will be, positive if it's off to the right, negative if it's off to the left. And the second degree of freedom has the pole angle, right? And so we can get the positions and velocities for each one of those degrees of freedom. You can reset it. You can apply forces to the cart using that single sort of linear degree of freedom. So yeah, it's the easiest possible way to work with the system. So when you're setting up a reinforcement learning example, you're setting up a new task. We have a very simple task framework. I hesitate to call it a framework. It's more like an example framework. It's not like something huge like PyTorch or something like that. But it's just something that eliminates a lot of the boilerplate code of stepping the simulation and stuff like this. So when you create a new RL task, you will create a Python class which inherits from this base task that we provide, and it has a couple of important callbacks, right? So first of all, you have a create sim callback, which is called to actually populate all the environments at the very beginning. So I won't be talking much about that because we already discussed a lot of these things so far. And then while the simulation is running, we have a pre-physics step callback, which happens before each physics step, which is an opportunity for you to apply actions, right? So your policy will produce some actions, and we will then convert those into some kind of physics engine input, whether it's applying forces or setting PD targets or something like this. So that will happen in that pre-physics step callback. And this is not per environment, this is for all environments, right? So this action tensor will hold all of the actions for all of the environments that will be applied together in parallel. And then in the post-physics step, the actions have been applied, physics simulation step has executed, and that's now your opportunity to get the latest state of the world, computer observations, computer rewards, figure out if there are some environments that need to be reset. And so that's where you would do this. So in the case of card pull, getting the observations is actually quite trivial, right? So assuming that we've acquired our DOF state tensor, we're refreshing our DOF state tensor so that copies data into the latest state snapshot into those PyTorch tensors that we have, and then we basically just we copy the DOF states into our observation buffer. Usually for non-trivial tasks, there's a little bit more work involved in computing the observations, but in the case of card pull, it's super simple. And really our states are just the linear velocity of the cart and the position of the cart, and then the angle of the pull and the angular velocity of the pull. And so that's all we're doing here. So it's super simple. Computing rewards is a little bit more involved, right? Because you now have to write some code that takes the current state and figures out what kind of reward to assign. And this is where things get a little bit interesting, because this is Python. We're writing everything in Python, but we're supposed to have this, full-on GPU pipeline where code actually runs on the GPU. And so if we were working with native code, we'd be writing CUDA kernels by hand here. And in fact, that's sort of how we started with Isaac Gym, right? Like we all wrote CUDA kernels by hand to compute all the observations, compute rewards, apply actions. Everything was a custom CUDA kernel. Now, that's a bit of a pain if you want to iterate quickly. I mean, it's good for performance. If you really, really want to squeeze the last bit of juice out of the hardware, that's good. But for day-to-day kind of RL work, you don't want to be doing that. And so the nice thing about PyTorch is that it has this torch script component, right? And you can actually JIT compile Python code to execute on either CPU or GPU. And so that's a little bit of magic that makes it possible to write, let's say, a reward function like this one here. You write it once in Python, but you can execute it on CPU or GPU. And so as part of our GPU end-to-end pipeline, we make use of Torch JIT script to actually run your reward kernels or observation kernels that are written in Python, run it directly on the GPU with very little overhead. Okay, so how do we apply actions in this case? Well, we need to apply, this is cart pull, right? So we need to apply a force to the cart. So each environment has two DOFs, and the first DOF is the cart, the second DOF is the pull. And so in this case, I'm simply I'm pre-allocating an array of or a tensor full of zeros, right? Which has two dimensions, one for the number of environments, the other one for the number of DOFs per environment, in this case, 2. And I'm setting the force for the cart, which is the first DOF of every environment, by taking my action, which is most likely normalized to something like between -1 and +1, and then just multiplying it by some constant, which we can adjust to give more or less force too. So yeah, so we've created this force tensor in PyTorch, but then we're passing it into this set of actuation force tensor function by using that wrapping utility that makes this torch tensor available to the GYM simulation core. Another useful thing to be aware of when you're working with GIM is that when you have multiple environments simulating in lockstep, some of them will get into a bad state, right? Which is kind of hopeless. Like at this point, the agent cannot recover. And so at this point, you can reset it, right? Like if in carpal, if your pole collapses all the way to the ground, it will be very difficult to get that back up into an upright position. And so, we can set a condition which will determine that, hey, okay, well, this environment's hopeless, we need to reset it. But when you have, 2, 5, 10,000 environments, we don't want to be applying resets to all of them if only a handful of them need a reset, right? And so for that reason, all of that control APIs that take tensors with the latest controls, and all of the state setting APIs also have indexed versions, right? So if you figure out a set of indices for environments that need to be reset, you can apply the new physics states or the new or a new set of controls to only a selected number of environments. And so we use basically an index tensor, which contains all of the environment IDs that need to be reset. We can then compute new poses, and we do that in reduced coordinates in this code snippet, right? So generate a random card position and a random pole position to reset this card to some sort of a sane state. And then we're applying the new states using the set.state tensor indexed variant of this function. So it actually takes an extra index tensor for the environment IDs to which to apply, and it will leave all of the other environments untouched. So that's the main sort of areas of the API. Hopefully that gives you an idea for how everything is put together. I know it's a lot to take in, so obviously we don't expect that you'll memorize all this stuff just from this presentation, but all of this is explained in more details in the documentation. So that's it for me. I'll take a look at the chat. If there are any questions, I'll be happy to answer them. Otherwise, I'm going to hand this off to Victor.
Thank you. Yes, there were a few questions not directly related to your talk, but more about support of flags and soft body simulation. So I can briefly answer this question before jumping into my part. So the version of flags used in SoftGym, it's based on the older public version of flags. Since that, we'll have a new version of flags used internally for the research and some of the reinforcement learning and robotic simulation. The paper, the project that Gabriel shared in his first video. So it has, this version of flags had a lot of improvements compared to the original flags version. So it's adding new types of solver and high fidelity Newton solver, support of soft body simulations that interments that was not available in the first version of flags, and full support, raw support of rigid body simulation and two-way coupling with soft bodies. So this version of flags was never released publicly, used for research, and it's integrated in Isaac Gym, but with quite limited functionality. Not all the functionality available. No liquid simulation, no high fidelity closed simulation exposed outside. So that's addressing one of the questions. Another one about availability of the functionality or features in PhysX or Isaac Gym. So PhysX team was working hard on implementing, improving all the research or work originally tried first or tested first in flags, as well as some new approaches. So this new work includes soft body simulation, NPM, liquids, and some more of the impressive stuff that we'll show at the end at New Frontier session, and Gabriel will speak in details and show some demos. Also, yeah, like Gabriel mentioned, there was a work in the different direction, in the direction of the differentiable simulation. It's while it's developed by Miles, and in some sense it could be called the successor of Flex, and his name Deflex. It's not. It's totally new research and new engine written, not even written in CUDA like original Flex. Using other approach and with focus on research differentiability and testing new ideas. So it's a bit like orthogonal, very like interesting and popular direction. It's a bit of orthogonal to the original Flex or to the soft body simulations that will be available, the new version of PhysX and in Omniverse.
Victor, there was also a question about whether LiDAR or IMU is available in current GIM or will be available in later versions.
So it's not available. Some support of LiDAR is in Isaac Sim, and also there is a way of emulate, maybe simplify model using PhysX recast, but none of this functionality is provided exposed in Isaac GIM. And when Isaac GIM will move into the Omniverse land and merge with Isaac Sim, all the functionality available in Omniverse, all the physics simulation, support for different sensors, LiDARs, it would be available. But not with in the current version of Isaac GIM and the upcoming.
As far as IMUs are concerned, I think we don't support an IMU object per se, but you can attach force sensors on articulation links at arbitrary local poses, and so that gives you the forces and torques experienced by the body at that location, and you can also get like obviously the body orientation and angular velocity and linear velocity, so you can get a lot of the type of information that IMUs provide in Isaac GIM.
Actually, there were just a few questions. Maybe you'll cover this. The questions from Fabio Moratore. Do the individual environments interact with each other? And how about the global physics parameters, like gravity, for example? Are they the same for all environments or different? So maybe at some point in your talks you'll cover.
So the gravity is actually a shared parameter for all the environments. At the moment, you can't tweak gravity in different environments independently. I guess you could say that is a limitation, but yeah, you just can't do it. And the reason for that is that at the core of this multi-environment setup is we're actually packing all of those environments into a single physics scene. They physically do not interact with each other by default, but you can configure collision filters in such a way that they do, or you can configure them so that, yeah, all actors from all environments will collide with each other if that's what you want, right? So you can have like a multi-agent simulation setup where the agents are actually, colliding and interacting with each other. But for performance reasons, especially on the GPU, it is beneficial to actually pack all of those environments into a single scene so that they're simulated together in lockstep, and you don't need to launch, an entire set of simulation steps for each environment, because that's very time consuming, right? Because the environments are very simple, and so you can't fill a GPU with just one instance of it. The speed up and the power of the system comes from the fact that we're actually packing everything into a single simulation. We're stepping everything together with collision filters enabled, and you can individualize each environment, the properties of the individual actors, but you can't really set global parameters like gravity different for each environment. I hope that answers the question.
It was very detailed question, so I can briefly add that it depends. I can't gravity as global property still can randomize, but having gravity individual per environment I think can be like avoided for many use cases, maybe only except some very special. So if you need to randomize properties, gravity properties, yeah, you can randomize gravity more often for all environments. You can add random forces using Tensor API for individual actors or links or rigid bodies that can emulate in some sense having additional forces acting on the system. And yeah, and you can have, I can show in my slides or as a live demo, I can show examples of having interacting different actors and agents, and you using collision filters and collision group mechanism, you can have a lot of even thousand agents interacting, or different robots potentially interacting with each other in the same environment as same. Or you can have a lot of individual not interacting at all.